Welcome to Bankable. I'm Doreen Abisundra, your host, and a proponent of innovative technology and financing solutions for AI infrastructure, decarbonization, and energy security. Like a sugar cube in your coffee, you drop it in, you stir it up, and it gets distributed throughout. A brilliantly clear visual of molten salt nuclear technology by our guest, Dr. Rusty Towell, Director of Next Lab. This is the first Bankable podcast to showcase a university nuclear research laboratory. Founded in 2015, Nuclear Energy Experimental Testing Lab, part of Abilene Christian University, and sponsored by Natura Resources, Next Lab is said to be building the first advanced nuclear research reactor. Natura Resources MSR-1 will be a 1 megawatt next-generation molten salt research reactor, with its technology described by Next Lab as essential to addressing the world's need for energy, water, and medical isotopes, while educating future leaders in nuclear science and engineering. Recorded August 14th, this podcast showcases one of the 11 technologies selected by the USA's Department of Energy's Nuclear Reactor Pilot Program, as announced August 12th. Natura Resources, alongside 10 advanced reactor technologies, will be supported by the DOE to streamline nuclear reactor testing in hopes of fast-tracking their commercial licensing. Why the interest? Well, if it all goes to plan, this research reactor could see its first deployment in 2026. That's next year, with a commercial facility sized to generate up to 100 megawatts of electricity by 2030, far sooner than its European counterparts. Plus, it'll be on track to supply the 5 times multiple of electricity demand which the International Energy Agency envisages by 2030 to match AI and global computing advancement. Commercial uses aside, as Dr. Towell highlights, no one uses a phone from 50 years ago. So why should our cleanest and safest form of energy still be based on technology from 50 years ago? Enjoy the insightful conversation. Welcome, Dr. Rusty Towell, to the Bankable podcast. Really fantastic to have you here. Looking forward to hearing a little bit about you, what you're doing, and how you're contributing to the world in nuclear energy. So, Dr. Towell, please introduce yourself and tell us a little bit about who you are, a little bit about your career history, and how you've come to be in the current place that you're at.
Well, thank you very much. Appreciate the opportunity to share about this exciting project. My name is Rusty Towell. I'm a professor in engineering physics here at Abilene Christian University. I'm also director of Next Lab, which is our nuclear energy experimental testing lab. So my background is from high school, I was intrigued by energy and what it meant to the world. I remember being intrigued by the strong force and how it has a million times stronger energy density than other forms of energy. And so far outpacing hydrocarbons or other renewable forms, if you can really tap into the nuclear force, you can free up a tremendous amount of energy. And so fusion and fission just intrigued me, and that pushed me into physics. And throughout my career, after getting my undergraduate degree, I was an instructor at the Navy's Nuclear Power School, and so I got very familiar with light water reactors and the what they were capable of doing and their safety record and how they could perform. And then I went into basic research. So professional career, worked at national labs, mostly particle accelerators, learning things that people really always ask the question, why do we care about it, right? Like your anti-quark content of the nucleon, and spin structure of the proton, those sort of questions that just, while intriguing and difficult, and that really stretched the ability to solve problems, it wasn't something you could say, and this is how it's going to make your life and my life better, understanding that. But after a few decades of working on those challenging problems, I became aware of really the opportunities in the advanced nuclear space. Why can't we yes, use the strong force, but why can't we use it more efficiently and safer and produce less waste? And the answer is we can. And there's a lot of ideas, but those ideas were put on the shelf 50 years ago, and basically our energy needs were met by other sources. But as we come back and we grow as as a worldwide population, and we expect more of our energy sources than we used to. We expect them to be clean, which wasn't a driving force 50 years ago, but now it is a driving force. We expect them to be safe, efficient. We don't want them to produce waste, and so we expect more of our energy source. And when you look at all that and you say, and we want it to be reliable, we want it to be dispatchable, you come back to there's really only one source, and it has to use that strong force. So what's the right form of nuclear? And so I started looking into it, and I found molten salt reactors and the blessings that the way that technology can bless the world. And that intrigued me and intrigued some other investors that started investing in a small project, and then it grew, and then the Department of Energy heard about it, and then an industry sponsor said they wanted to sponsor it. And then all of a sudden we find ourselves from a crazy idea a decade ago to being one of the leading advanced nuclear projects in the nation here in the United States. And so very thankful for the opportunity to do this, because it's exciting to work on something that's, yes, challenging problems, but also is going to bless the world.
How incredible. What an incredible insight you bring to this topic. So maybe let's go straight into now, what exactly is that next lab that you've just spoken about? Maybe even tell us a little bit more about ACU and how that links in with Next Lab, what the technology is that is being created in the Next Lab, and why is it of interest? And obviously, there's a lot of knowledge sitting with you. So if you can take us in with a bit of a layperson's description, please.
You bet. Well, there's a lot there, so let me start unpacking it. When I forget a part, you can chime back in. And so, Abilene Christian University is a university that has a mission of educating students for Christian service and leadership throughout the world. And so that's sort of what we're about as a university. And so why advanced nuclear? How does that pair with the university? And the answer is the mission of Next Lab is that we want to address the world's critical needs for water, clean water, for clean energy, and for medical isotopes to diagnose and treat cancer. And we're doing that by developing molten salt reactor technology while educating the future leaders in nuclear science and engineering. So that's our mission, and that's how we live into the ACU mission, and that's why ACU is really focused in funding this. And I'm standing in a $23 million facility that ACU built, and it is the world's first advanced reactor prototyping center. So Idaho National Lab is bringing online a couple facilities later this year, next year. They're very proud of to prototype some advanced reactors, and we're excited about what's happening at Idaho. But this building was finished and we moved into it 18 months ago. So we are already in that sort of facility, and that's sort of the buy-in and vision that ACU's lived into this. So what is this? I told you molten salt reactors, and really what we mean there is we're still using a strong force. We're still talking about nuclear fission process, but what we're doing is we're just taking the technology that's been used around the globe for the last 50 years plus, and we're trying to advance it. We're trying to bring it in the modern day, right? I mean, no one uses a phone from 50 years ago, so why should our cleanest and most safe exciting form of energy still be based on technology from 50 years ago? And so how do we do that better? We do it by changing really only two things. So the fluid that moves the thermal energy, the heat, from where it's produced in the reactor core to the steam generator that makes steam, that turns a turbine and produces electricity, the fluid that moves the thermal energy, we're upgrading. Instead of just using water, we're using another fluid. And that's the fluid we're using is salt in a liquid form, so we call it molten salt. So at room temperature, we're all familiar with table salt, sodium chloride, it's a solid. It turns out if you just raise the temperature on that salt, really, really high temperature, it'll actually melt, just like ice melts and becomes a liquid. The same thing happens, it just happens at much higher temperatures. And so the beautiful thing about using molten salt is we can operate at really, really high temperature and low pressure. And so current reactors around the world, the 400 plus commercial reactors that are sort of deployed around the world today, most of them are water. And if you use them water as your coolant, then you have to have it under high pressure. And so we refer to them as pressurized water reactors. And that's really the danger, right? I mean, the danger that's inherent to them is it's a very, very high pressure system. And we're using a fluid that if it leaks out of that system, it immediately wants to flash to steam and expand and rise. And so if you have an unbelievably bad event, like a horrible earthquake followed by a horrible tsunami, and you lose your backup electricity. So I'm talking about what happened in Fukushima in Japan, a horrible accident where tens of thousands of people were killed in the earthquake and tsunami. But in that situation where you lose backup power, how do you relieve that pressure? Well, if you vent it, it becomes high temperature gases that's leaked out. That separates the water, H2O, into hydrogen and oxygen. If you have a room full of hydrogen and oxygen, you're just waiting for a spark, and then you have the explosion. So that was the explosion we saw. It was a chemical explosion around the reactor, but it's all based on the high pressure that's there. And so what if we were able to remove that high pressure water and replace it with a fluid that never wanted to boil, never wanted to expand to a gas? It always stayed in a liquid form. That's what we have with molten salt. And so we can operate at very, very high temperature and low pressure. And so that's the beauty of using, and all we've done is we changed the heat transfer fluid, right? And so we basically, if you do have a leak in a molten salt system, it's more like the wax on the top of your candle. If you turn your candle sideways and that wax that's in the heat flame that's warm and it's a liquid, it spills over the side. As soon as it gets out of that heat source, it starts to freeze, and it freezes. And if it's a slow leak, it doesn't even drip all the way down. It just sort of oozes off the candle and freezes on the way down. Even if it's a rapid leak, the molten salt will fall to a catch pan and freeze there. Nothing expands and goes up in the atmosphere, drifts around the globe. It falls down. And so that means you don't have to have safety system on top of safety system on top of safety system, because it's inherently safe. And so a lot of talking, but the technology we're talking about is it just makes nuclear power safer and cleaner. Let me talk just a little bit about that part, because that's a huge part of the technology also, is and this is the second change we're making. The 100 plus reactors in the US and 400 around the world that are commercial reactors, they typically use water as the coolant, and they put the fuel, the uranium, in a ceramic form, and they put a metal cladding around it, and they make these fuel rods, and all of the radioactive material is designed to stay inside that metal cladding. And if it does, then it keeps the radioactive stuff away from people in the environment. And so that is their safety mechanism. The downside of that design is that when that fuel rod is no longer able to fulfill its mission inside of reactor core, because you build up fission fragments, or the cladding becomes unstable or whatever, you take that fuel rod out and you call it spent nuclear fuel. And so what used to be an asset, fuel, is now a liability, and we call it waste. Well, in that solid fuel waste, we still have over 90% of the energy content that was there originally. We're essentially throwing it away. And not only are we throwing it away, we're saying this is radioactive material that we need to store for the next 100,000 plus years, which is really hard for me to get my head around, 100,000 years. And so why do it that way? There's a better way. And so the better way is, instead of making solid fuel rods, let's just take our fuel, same uranium, but let's put it in a salt form, so uranium fluoride, and let's dissolve it in the molten salt. So think of a sugar cube in your coffee. You drop it in, you stir it up, and it gets distributed throughout. And so the fuel is distributed throughout the molten salt that's in the core. And what that means is several things. One, from a safety point of view, if we shut down the reactor, we can remove the fuel from the core. So we're not counting, or we're not relying upon control rods going in and shutting down the reactor or something like that. We're literally taking the fuel out of the core, which guarantees it's shut down. And what does it take to remove the fuel from the core? Gravity. So as long as gravity works, we can shut down the reactor. And so we can call it a walk-away safe reactor, because literally you can walk away from it and it'll shut itself down. The other thing it does is we use all the fuel. So none of the fuel gets left in a fuel rod and gets thrown out and spent nuclear waste. So you increase your fuel utilization while simultaneously decreasing what goes into the waste stream. So again, a win-win situation.
That's just phenomenal, because you've just addressed two of the key topics that come up every time. For example, even today I was walking down the street and my neighbor said, "Oh, remind me what you do. And I said, oh, nuclear energy. And she went, oh, it's so dangerous, so unsafe. And, what happens if there's a spill, and what do you do with that fuel? So you're effectively saying this technology that NextLab is developing, firstly, does not need to be stored when it becomes so-called waste, or rather there isn't any waste. And before that the cooling happens naturally, because it's a molten salt, and which doesn't need to be pressurized. So you don't need that extra energy for backup. Incredible. That's so fascinating. And tell me, so how is NextLab? How did NextLab rather come up with this idea? Because there's so many different forms of nuclear technology that are being considered. How is it that you've come to this stage?
No, it's a great question. And so, my background is nuclear physics. And while I have an understanding and taught about pressurized water reactors, I really, was interested in solving problems. And when I became aware and encouraged to look into advanced reactors, you're right, there's a lot of different forms of them, a lot of flavors out there. And if you look at the number of companies, I think the last count I heard, it was over 200 different advanced nuclear companies. I mean, it's amazing the number of companies that have sprung up with this goal in mind. And so what's the difference? Well, first of all, let me just say fission versus fusion. They're both nuclear forces, and they both have, they both take advantage of, Einstein's equation equals mc squared, where just a little bit of mass converted to energy produce a lot of energy. So from tiny pellets of matter, we can produce tremendous amounts of energy. That's beautiful. But fusion happens in the sun and in stars, and it can happen in sort of fractions of a second. We can sustain it here on Earth, but we have never demonstrated the ability to harvest energy from fusion. There's a lot of work on it, and it's an exciting future. It's what got me excited when I was, a teenager in high school, a whole bunch of decades ago. But at that time, they said, fusion's probably 40 years away. And, now I think an honest assessment is fusion is probably 40 years away, which I realize in saying that nothing's changed. It's a challenging, hard problem. We should work on it. But the idea that someone says we're going to power a data center in 2 years using fusion is not a bankable investment, in Rusty's opinion. So I'll borrow your words and put that's my opinion. It's an exciting, it needs to be studied in the lab. But what can we do about our problems today? How can we address the energy world needs today? We definitely have to go with fission. So what type of fission? So you want water cooled? No, we've said that has problems. So we think about alternate coolants. Well, you can do high temperature gas. Well, that gets you to high temperature, but that's high pressure also. And so it has that same problem. So you can say, well, what about metal, like sodium or even a lead bismuth or something like that? Well, sodium is very, very, very reactive. And so, if you ever have a problem where it leaks out, you have a real problem or have the potential of having really bad chemical reaction. And so maybe that's not the best solution. And so you keep looking through them and you say, molten salt gives us what we want, the very, very high temperature, but the low pressure. And then if we can combine that with the liquid fuel aspect, then we have the advantages of decreasing the waste we produce. And I haven't talked about it yet, but when you have that fission process and you produce when the big uranium nucleus splits up into 2 little fission fragments, some of those fission fragments are life-saving medical isotopes. In old design, they're stuck in the core of a pressurized reactor. In our design, they're floating around in the salt. And if you can find a way of pulling them off, then doctors have a new tool to treat and diagnose cancer. And there's some amazing targeted alpha therapies out there that have shown extremely great promise at defeating multiple types of cancer. But the problem is, and every study that's ever been done on them is, this is amazing treatment, but there's just not a source of this isotope. Well, and the reason is because those isotopes are made in, core of stars and core of pressurized reactors. And neither one of them can you get those isotopes out in hours or day time frames, which is the half-life of those medical isotopes. So liquid fueled gives us access to those medical isotopes, which again gives doctors a tool to really, treat and in a lot of studies cure cancer in different forms. And so it's just an amazing tool. So we believe the right technology, and that's sort of where we landed, about a decade ago, is that we want to go with liquid fueled, molten salt cooled technology. So we started in ACU with a small system. Can we melt the salt? I'd never seen melted salt before. So let's melt salt. And then we want to build a system out of it. So you need things like pumps and valves and flow meters and temperature sensors and pressure sensors and just those nuts and bolts, which, again, if it's a water system, I can walk over to a hardware store and buy the pump and the valve and the pipes and have it built this afternoon. But we're talking about a fluid that wants to operate at like 600 degrees centigrade. And so it's extremely high temperatures. And so everything's a little more challenging. So that's where we started, was just, can we build those nuts and bolts of a high temperature system? And we've learned a lot. And then from there, the Department of Energy in the US heard about what we were doing, and they came to us and they saw our first little salt loop we had. And they said, this is an amazing little toy, they called it a research project in the lab, and students are working on it. It's very exciting. And we love your vision of taking this technology and blessing the world. How do you go from a little research project to actually blessing the world? And we were invited by Department of Energy, please come to Washington, D.C. and tell our whole team what your plan is. And so at that moment, President Schubert, president of ACU, and I got on a plane and went up to Washington, D.C., and we talked to him. Along with us was one of our biggest donors to the project. So Doug Robison was a donor. He had pledged over $3 million to this research project. And so we met with Department of Energy, and we said, our path is we want to build a university research reactor. And at that time, the Department says, you have to do that. We definitely need it. The world's moving forward. China has visions of doing this, and we certainly would like to move forward. And so we want you to do this. And we said, well, if you'll provide the fuel like you do for all the U.S. research reactors at universities, we'll do this. And they said, yes, we'll commit to doing that. And so at that point in time, the three of us, how are we going to do this? And President Schubert and Doug talked, and President Schubert said, Doug, will you figure this out? And Doug said, okay, let's figure it out. And he went out and figured it out. What it looked like is to deploy this to the world, to take this technology beyond a research reactor and deploy it to the world, we need a company to do that. So Doug stood up Natura Resources, a company whose mission it is to take this technology that's being developed and researched here at ACU and Next Lab and take it to a commercial scale and deploy it commercially. And so Next Lab, which is a research project at Abilene Christian University, is funded or powered by private investment from Natura Resources. And that's the origins of how we got here.
That's just such a fascinating, but also enlightening and inspiring history that has brought you to where things are. And two things in particular that struck me was the use of the nuclear power. So not just energy for data centers, which is that that buzzword these days. And obviously, we are going to need even more, an exponential amount of energy to fund the AI advancement that we're seeing here. Not a single nation seems to have a national infrastructure plan to match the 2 to 5 times more energy that we might need even by 2030. So that's a fundamentally interesting angle. But I'm so glad that you mentioned this bit about medical isotopes. And maybe if I can just ask you to just go through that a little bit again, because here in the UK, we do have some programs that are looking to develop and harness the isotopes. One of the key cancers that is being considered is prostate cancer, which affects so many people and so many gentlemen that could be easily treated with the innovation. So tell us a little bit about how you harness a medical isotope in the context of the technology that you have.
Yeah. So one of the way the nuclear process happens, right, is you have a neutron gets absorbed by a very large, close to being unstable nucleus, and when it's absorbed, it becomes unstable and breaks into parts. It fissions. Sometimes a neutron is absorbed and it stays stable and absorbs another neutron, and it keeps changing. And so the isotope, the structure of the nucleus is changing in this environment, this neutron-rich environment. And so there's multiple paths to producing these radioactive isotopes. And so normally people hear radioactive isotopes and they think, oh, radiation and danger. Well, yes, but there's radiation all around us. And if we use the right form in the right place, it can literally be lifesavers and that's why we treat certain forms of cancer and things with radiation therapy. The challenge with traditional radiation therapy is you end up really hurting healthy cells as you're trying to kill the cancer. And so it's in a very crude analogy, it's like the World War II strategy of bombing, right? You go into a city and you just carpet bomb the whole city in order to take out the enemy military, right? And so that's sort of what's happening with current treatments of radiation therapy is we're using betas and gammas, which penetrate hundreds or thousands of cells to get to the one cancer cell. And so there's really no way of targeting the cancer over other things. Now, the other form of radiation that's out there is alpha radiation or alpha decay. And so if you're the beautiful thing about alpha particles when they decay is that they pack a huge punch, but they don't travel very far. So normally people are telling you about the different radiation. Gamma rays can penetrate through a very large, thick metal or concrete walls, and betas can go through a smaller distance. And then they talk about alphas, and they hold a piece of paper and they say a piece of paper will stop an alpha particle. And that's the beauty of it, is that you attach that alpha emitter to basically some sort of antibody. And now I'm talking about medical stuff that I'm not that kind of a useful doctor, but I can describe the process. Is you take this ticking time bomb of an alpha emitter, you attach it to an antibody. The antibody is injected into a person. The antibody goes to the cancer, and so you basically deliver this alpha emitting atom right next to or inside of a cancer cell. So when it alpha decays, you emit this alpha particle, and it travels not through hundreds or thousands of cells, but through one or two cells, and it kills them. It does enough damage in that one cell that it prevents the replication of the cancer cell. So literally, you kill the cancer cell and do nothing to the healthy tissue. And that's what doctors refer to as targeted alpha therapy. And so think smart bombs versus carpet bombing, right? And so with thousands of times less radiation to a patient, you actually more effectively kill the cancer. And so, yes, for prostate cancer is a number one application of this targeted alpha therapy. And again, we just need more of these alpha emitters, because that's literally probably the most expensive element or isotope in the universe. Is if you can produce those actinium-225, then you can save lives with it today. We just need to produce them. And so with this technology, can we develop a system where, as a byproduct, as you're producing electricity that's clean and safe, can we also be producing actinium-225 or other alpha emitters that will actually save lives? The answer is yes, you can do that. So it's a weird combination to say we're going to provide electricity and we're going to cure cancer, right? And so I mean, it's almost too good to be true, and it really is. It's a technology that's too good to leave it on the shelf.
What an absolutely incredible combination there. So maybe now it brings back to where the reactor size could be once this technology is tested and gets to be at a level that's commercial. Are we looking at perhaps a 1 megawatt, much bigger than that, or even gigawatt scale? Where do you stand?
So this, one of the beautiful things about this technology, it's very flexible and scalable. So yes, you can make a very small. We're making here at ACU. We have a construction permit from the Nuclear Regulatory Commission to build a 1 megawatt thermal research reactor, and so we're building a very small megawatt size reactor, which again fits in that micro or small modular reactor type this thing. And so you can build it that size, but you can also scale it all the way up to gigawatt scale size, or more realistically, probably the sweet spot is where everyone thinks the future is small modular reactors, right? Let's build a reactor in a factory where you have the high quality but low cost mass production of these things. And if you need, if you, for Natura, for example, is talking about building a reactor that's 250 megawatts thermal or 100 megawatts electric. And so if you need a gigawatt, you grab a dozen of these, 10 or 12, and put them together in a group and operate them as one power plant. But that allows you to sort of mass produce the same thing, and if you need half that, well, then great. You put 5 or 6 in an installation. But it allows you to deploy rapidly, high quality, safe, common design reactors that will go and meet the world's needs where they're at.
It's fascinating, and really, really fascinating there. At this point of time, and obviously because this is a podcast that focuses on financing, I usually ask the guest to tell us a little bit about their so-called financing journey. And Dr. Tal, you briefly touched upon that with your financial backyard, but maybe go a little bit into depth as to who has funded it, if it's beyond the gentleman that you'd mentioned, how much more you might possibly need, if at all, or thirdly, kind of why was it deemed bankable by your very first investor?
Yeah, so early on, ACU received donations. So some local foundations, some local individual investors that loved the vision and the mission and really supported that and helped us get going. When Doug Robinson heard about this, as I mentioned, he very rapidly understood the value of energy from his background and the value of nuclear power, again, from his history and sort of look into future energy sources. And so he could quickly evaluate the bankability, that's a new word maybe, of this project. And he gave $3.2 million to the university to support this vision early on. After we met with Department of Energy and they agreed to provide fuel, and we realized that we needed to move beyond just a research project or even a research reactor to deploy to the world, that's where he stood up Natura Resources. And so at that point, this project transitioned from being supported by donations primarily. We still accept donations if you want to help. But the primary source of funding came from Natura Resources. Initially, that was Doug Robinson funding it out of his own pocket. He's since grown a group of investors that believe in the mission, believe in the project, and want to yes, get a return on investment. That's a part of an investment, but also understood how this was going to bless the world. Since that time, Natura Resources gone through multiple rounds of funding. They continue to raise money as need be. Most recently, the state of Texas approved $120 million to focus on desalinating water from the oil fields of West Texas and to advancing this project. And so the state of Texas has said this is very, very important. Just this week, the Department of Energy selected Natura Resources for part of their pilot project. And so the Department of Energy is trying to push us forward also. So the financing has come from private dollars until the state of Texas has also come alongside. But investment dollars are the right discussion is with Natura Resources, and you can find them easily online and get in touch with them if you want to reach out to them. But that's the mechanism of investing in this project. And yes, they're still raising capital. And while we're talking about this research reactor, Natura is also looking beyond that to commercial deployment and the need to meet the world's energy needs, the energy needs in Abilene, the state of Texas, the U.S., and the world, right? We all have it. As you mentioned, there's nobody that has the future energy solved. It's a need around the world.
Gosh, yes, indeed so. And I think we've really hit the nail on the head there with the fact that we need that combination of government funding, but also commercial and individual funding. We need to just bring that. And you're right, bankability is a word we tend to use in the finance world. So brilliant. I'm glad you're on that track. Just maybe curious on the fuel. You mentioned the Department of Energy provides the fuel. Tell us a little bit more about that fuel, because from a very layperson's perspective, we're talking molten salt. So tell us a little bit more about that fuel, and also why the so-called there isn't as much waste, or any waste, if I heard correctly.
Yeah. So why are we asking Department of Energy to provide fuel for us, or why are we going down that route? We started this project, unlike many other companies that start out with either a huge grant from the federal government or perhaps a billionaire bankrolling it, something like that. We started out with a relatively modest investment, but we've been wise with how we spend it, and we've done a lot of small things in parallel that has allowed us to move forward to where now we're one of only two construction permits in the United States that have been granted from the Nuclear Regulatory Commission to build an advanced reactor. And so we're very excited about being sort of the tip of the spear of advanced nuclear in the country. And we've done that because we've been very smart in where we've invested and how we've moved the project forward. And one of those strategic plans was, let's build a university research reactor. Of course, we need to train the next generation of workforce. We need to collect the data from a small demonstration reactor. So from Abilene Christian University point of view and the Nuclear Regulatory Commission point of view, we're building a research reactor according to the official definition of a research reactor with the NRC. But from a business point of view, this is a demonstration reactor for Natura. It demonstrates you can get a license, you can build it, you understand the technology, you understand the materials and all the challenges there, and you can scale up to commercial. And so from Natura point of view, this is a demonstration reactor. And so that it's important to their business development path. It's also important to ACU. If it's a research reactor, the United States has about 25 research reactors at universities around the nation. All of those get their fuel from the Department of Energy. Long ago, the federal government decided every university that wants a reactor probably shouldn't be stewards of enriched uranium and be responsible for disposing of that at the end of their life. And so they made the sort of decision that that fuel would be owned by the Department of Energy, loaned out to the schools to be used, and then brought back. And so that if we were just build another pressurized water reactor here, or solid fuel water-cooled reactor, a trigger reactor at ACU, there would be no question, yes, Department of Energy would provide the fuel for us. The question we asked the Department of Energy back in 2019 is, we're a university research reactor. We would like the federal government to own the enriched fuel, and we would like at the end of life to say the federal government will help us dispose of it safely and properly. But it's a different fuel form. It looks different. It's not a solid fuel rod that goes into a trigger reactor or some other sort of pool type reactor that's most common at universities. This is advanced reactor technology. And so we have a different fuel form. And so yes, we need uranium, the same uranium-235 isotopes, but instead of in a, some sort of ceramic oxide form surrounded by metal cladding, we want it in a uranium tetrafluoride form, a green salt. It's another form of salt. It looks green to the eye, and that's the form we need it in. And at the end of life, we're not going to just hand you back a spent fuel rod. It'll be a different form also. So was and is the tricky question of how do you produce, transport, dispose of a different fuel form than what's traditionally been done. It's not a difficult thing. It's just something we haven't done the paperwork on before. So we need to answer a lot of paperwork questions. And there's some R&D questions there. What's the right shipping container? Well, let's make sure we get it approved. So when it's being shipped, if there was an accident, it's safe, et cetera. So there's necessary steps there, but they're just sort of administrative and engineering steps that need to happen for something new.
And you got me thinking, presumably you're using AI to help with the research and the answering of those paper-based questions. Would that be fair to say?
I mean, where we can, we're certainly taking advantage of it. And so, yes, there's places where AI makes everything easier these days. And so we're certainly trying to be smart about how we do that.
Okay, fantastic. And this is maybe on the tangent, but where does the term digital twin come into play, if at all?
Yeah, so generically, a digital twin is just if we really understand something and how it works and behaves, we should be able to make a model of it. And so it's just a computer model that mimics real life. And so, whether a lot of video games are just sort of digital twins of gravity and friction and real world things. So you can play games where you throw a ball and you understand the trajectory and, and so that's a digital twin of reality. What we're talking about here is, do we understand the processes and what's happening, the physics, the neutronics, the thermohydraulics inside of this new design reactor well enough to model it? And so one, it gives us confidence that we understand the physical processes, but then can we start using it and collecting data so we can start doing predictive things in order, what's the best way of operating it? Can we predict when different elements might need maintenance? And so we can do preventive maintenance ahead of time using predictions. And so that's the exciting parts if you're talking about how commercial development of these reactors and using a digital twin to help us operate those things more efficiently. That's the kind of exciting thing in the future. But it starts with just really simple things of, do we understand the physics of what's going on there and all the different chemistry that's happening inside the reactor? Can we model it? That's your digital twin.
Incredible. And you've described so many of the incredible options that come out from this new technology, from not just electricity, but also to medical isotopes. At that point about desalination, I'm so glad again that you mentioned that. We're starting to see that in certain countries in the Middle East using nuclear energy for desalination. Fantastic new ways of looking at so-called additional revenue streams for a nuclear facility. So if I ask you this question, and the answer is almost very clear, but so how is NextLab and the technology contributing to either decarbonization, AI infrastructure, and/or energy security?
I think it is the answer, and I think it is the only answer is nuclear. Because if we want to decarbonize the electric grid and beyond electric, right? There's a lot of big manufacturing plants where the electricity is only 10% of their energy needs because they're heavy refining or chemical processes, whether it's fertilizers or plastics or petroleum refining or foundries. There's lots of industries, they need high temperature thermal energy. And currently the way you get that is burning hydrocarbons, right, is really the answer there. And so if we want to decarbonize the industry or the energy needs beyond electricity, you really have to go to nuclear to do that, because nuclear truly is, there is no smoke stack, there's no CO2 coming out, and it's dispatchable, right? Meaning we tell it when we want to turn it on and when we want to turn it off. AI centers don't like operating when the sun's up and turning off when the sun goes down. AI centers don't like operating when the wind's blowing and when it's still turning off, right? AI centers, hospitals, chip manufacturing, big plants of any sort, no big plant likes to turn on and off, on and off. Everything likes to run. Personally, I like my air conditioner run 24/7. West Texas is a hot environment. We like to have our air conditioning on all the time.
I remember the summers out in Abilene, indeed so. Mm-hmm.
And so reliable dispatchable power that is carbon free, the only solution is nuclear. And so if you're going to do nuclear, can we do it safer and cleaner and more efficiently than we've done it in the past? And the answer is yes, we can. Molten salt liquid fuels gives us all that.
Brilliant. And when can we see this technology being available from an operational perspective?
Yeah, I mean, the answer to that is soon, and sooner probably. If you'd asked me 6 months ago, I would have said Natura is talking about a 2030 commercial deployment. But with all of the interest and push and initiatives being selected this week by Department of Energy to be part of the pilot program, with part of that program is, can you have a reactor operational by July 4th of next year, right? I mean, that's President Trump's bold vision or what he's asking to do. And so with the right support, Natura has a path where they can have their molten salt reactor 1, which is our research reactor that we're building here at ACU. We could have it operational next year, which would then collect the data and allow Natura to move and scale up and have a commercial deployment before 2030. And so there's some exciting things happening. It's going to happen. It's going to happen faster than I think we originally thought it would happen. But it's really just it comes back to, how much capital can we invest in this and how quickly can we do how many things in parallel. So as we're building and commissioning this research reactor, Natura's demonstration reactor, how far along are they already in the design for their commercial reactor? And that's a question of how much capital is being invested in the project.
Okay, gosh, that's just quite fascinating. Next year, 2026, because you're absolutely right. Next to almost everyone says, oh, SMRs, advanced modular reactors, these are the 2035, 2040 topic. This is far quicker. Very incredible. And what makes you so, assuming you get that capital, what makes you so confident we can get there within the year?
Well, I mean, in the past, the question, the questions that really drove the pace was the how fast can I get a license? And we submitted in 2022 our construction permit to Nuclear Regulatory Commission. And at the time, I think the guidelines was something like 48 months, right? 4 years to review that. The NRC promised a 2-year review, and they did it in 2 years. But that's just step one, ability to build the reactor. We then go back and ask for an operating license. So we have been assuming there would be a 2-year from when we submit the operating license review period. Well, with all the encouragement and resources and focus on being timely reviews, that's been shortened and shortened by the Nuclear Regulatory Commission, where they're shortening the review times. So instead of being 2 years for the construction permit plus 2 years for an operating license with some time to answer questions in between them and stuff, and so it's a 5 or 6 year process, now they're saying, maybe we can get those reviews in under a year or under 9 months. And so all of a sudden that timeline is being shortened. So now it's not a question of how fast are they reviewing our applications, but how fast can we write them and how fast can we build the things. And so it's sort of back in our hands. The schedule is more under our control than it has been in the past, perhaps. And listen, lots of things have to go right. It's a tough and challenging, and we're doing something that's never been done before. So with all those things, it's hard to anticipate all the challenges that are there, but there is a path, there's a way of doing it, and there's more and more support for it than there ever has been. And so I'm very optimistic that we're going to move forward faster than we thought would be possible.
That's just so enlightening and exciting at the same time. So effectively, the regulation is going faster than previously. The technology is moving ahead based on the research and the activity that you guys are doing. So ultimately, it's just the capital that's needed, the funding that's needed for this market. I'd like to think that based on this incredible insight you've given, that there'll be investors knocking your door down. So fingers crossed on that. Brilliant. Well, this has been, we could go on for a couple more hours. I think there's just so much knowledge that sits there with you, Dr. Towell. Thank you for sharing it. I do think I have to give a shout out to my professor, Dr. David Merrill, who brought the attention of what ACU and NextLab is doing to me. So we have to give him a shout out for that. But where and how can the audience contact you and hear more about the incredible work that you're doing?
So our website, acu.edu/next, will tell you more about our project and more resources there. Obviously, if you want to donate, we're welcome to, and we're happy and excited to receive that. If you want to invest, then talk to Natura Resources. So naturaresources.energy will take you to their website, and you can contact them about an investment on the Natura Resources side. We're excited about the project. We think this is a technology that's been on the shelf for too long. We're excited about bringing it off. We know it's going to bless the world, and that's what gives us really energy to keep working forward and keep moving on it. So thank you for highlighting us. I appreciate you having me on today.
Oh, brilliant. Fantastic. If I give you the absolute last word, is the technology that NextLab is developing, is that bankable? What, yes or no?
Yes, absolutely bankable.
Brilliant. Fantastic. Dr. Towell, it's been an absolute pleasure speaking with you. Thank you very much for your time, and looking forward to seeing the operational plant. Thank you.
Thanks. You're welcome. Come visit anytime.
Thank you for listening to Bankable. For early access to energy transition pioneers and to learn how to structure the investment solutions described in this episode and throughout the series, subscribe to the podcast and get in contact at frescocleantech.solutions.